Now we are going to begin a very important topic in analysis. This is continuous functions. So you've probably come to think of continuous functions in this intuitive way. You can draw them without picking up your pencil. So now let's put down a precise definition. So let's let x be a subset of the real numbers. So this is the set where your function is defined. We're going to let a be a point in x, and f is a function whose domain is x and whose range is the real numbers. Then we say that f is continuous, and I should let you know I'm going to say this so often, CTS is the abbreviation for that, at a if whenever we have a sequence of points contained in x, which converges in particular to a. We also have that if you take the sequence of f of xn, that's another sequence of points that also converges, and what it converges to is required to be f of a, and that's what it means to be continuous at a point. And let's see what this looks like. So here is our set x, and here is our point a in x, and then our function f of x. Here is f of a. And the idea is that whenever you've got some points that are getting closer and closer and closer and closer to a, their images are getting closer and closer to f of a. And I want to emphasize one thing that's maybe not quite you're used to. Let's let our x be this closed interval from, let's say, -5 to 5. And let's let f of x be the square root of 25 minus x squared. And you probably remember what this looks like. Here it is the graph. Here is the graph of this thing. Here is our region x, and then the graph is a half circle that goes like that. And notice in particular that this function is not defined when x is bigger than 5 or smaller than -5. But what I want to emphasize is that we still say that f is continuous at 5, because we only care about sequences that are in x, that are urging to our target point 5 here. This sequence over here, notice that f of x doesn't exist for these orange points, so certainly f of x is not converging to f of 5, but at some level we only care about what f is doing for points that are in x. So this still counts as a continuous function, even though we've got this half open and business going on. Now, one convenient part about this definition of continuity in terms of sequences is that we can take all of our propositions from section 1.3 about convergent sequences and get from them we can very easily get theorems about continuous functions. So, for example, this proposition follows straight from proposition 1.3.6. Let's let A be a point in a set X that's a subset of R, and let's let F and G be two functions. Both of them have domain X and range the real numbers. And let's suppose both of them are continuous. Then we get the following things are true. So first thing is that the function f plus g is also continuous at A. Second thing is that f minus g is continuous at A. And then the third thing, actually, the second one is that f times g is continuous at A. The third one is that quotients are continuous. Now, if you remember proposition 1.3.6c, that only works if your denominator is eventually not zero. And a little while later, we'll be able to talk about conditions where we can force the denominator to eventually not be zero, force g of x sub n eventually not to be zero. But for now, let's just say g of x is not allowed to be zero for any x in the domain, and as long as that is true, then the quotient f over g is continuous at A. And so let's mention a couple of particular functions that are continuous. So all constant functions are continuous. And also the identity function, that is the function I of x equals x, that is continuous. And it sort of doesn't matter what you pick your domain to be, this is going to be continuous anyway. And the proof works like this. So let f of x be c for some c in R, and this is meant to be true for all x in x subset of R. If A is in x and xn is converging to A, then f of xn equals c. So f of xn converges to c, also known as f of A. So we see that constant function is continuous at any point, any particular point you want. Now let's move on to the identity function. So let's let I of x equal x. And that's true for all x in whatever you want to think of your domain as. Can be all of the real numbers. Sometimes it's convenient to think of it as a subset of the real numbers. And then if A is in X and Xn converges to A, then f of xn, which is equal to f of x, which is equal to xn, not fi of xn, then that, of course, is converging to A, also known as I of A. So our identity function I is continuous at A. And then we can put this together with the proposition 1.7.2 and get a corollary. And that's that all polynomials which, remember, is functions you can write as f of x is a constant, and then a constant times x, and then a constant times x squared, up to the nth power. Well, the function f of x equals x is continuous. You can multiply that function by itself as many times as you want, so you get that x squared and x cubed and x to the n, they're all continuous. You can multiply by constant functions because those are continuous. You can add them all up. So the point is you can start with the things the absolute basic building block functions that we saw in the last proposition. You can put them together in ways proposition 1.7.2 lets you do, and you end up with you can get polynomials that way. So all polynomials are continuous. And then rational functions. A rational function is a function that you can write as a polynomial over another polynomial. These guys are continuous if you restrict your domain, if you throw out all the zeros in the denominator. Then you are continuous. Let's have another proposition that lets us put together two continuous functions to get a continuous function. Now, in this case, our conclusion is going to be that we want to say that compositions of functions are continuous. So we want to conclude this proposition by saying, therefore, the function g composed with f is continuous at A, and in case you've forgotten, recall that the function g composed with f this is the function where g composed with f of x is g of f of x. So you evaluate f and then you evaluate g. So for example, the function sine squared x, that's squared composed with sine of x. You take the sine of a number and then you square it. So let's see what we have to write down at the start of the proposition so we can conclude that g composed with f is continuous. Let's let y be a subset of the real numbers and g is a function from y into the real numbers. And let's let x be another subset of the real numbers and f be a function defined on x. So far we've just got two functions, g and f, and their respective domains, y and x. But we want to talk about g composed with f. That means we want to take f and then take g of it. So turns out we need f to map f from x into y. That is, any x, f of x has to be in y so that g of f of x will be meaningful. And then we let a be a point in x. And now we're supposing that f and g are continuous, so we suppose f is continuous at a, and then g is continuous at f of a. And then the conclusion is that g composed with f is continuous at x. And let's draw a picture. Here's the real line. Here is our set x. Then here's the real line again. Our function f is sending x to some set in here. And we're going to put y as the domain here, and then here is our function g that sends y to something in the real line. And then we've got our point A, which goes to f of a, and then g sends that to our point g of f of a is g composed with f of a. And hopefully this will help you see why we've put these restrictions on x and y and so on. Then the proof is reasonably straightforward. Let's let xn be a sequence in x. Xn is converging to a. And then f maps from x into y. So this sequence, f of xn, each xn is in x, so each f of xn is in y, and then f is continuous at a. So if xn goes to a, that means f of xn goes to f of a. And then g is continuous at f of a. So if you've got any sequence that converges to f of a, including f of n, so your g of f of xn, g of a sequence converges to g of f of a, or g composed f of xn converges to g composed f of a. And that it's all there is to that. That is what we mean for G composed with F to be continuous at A. Now we are going to prove something called the extreme value theorem. And this is a very useful theorem. So let's let E be a subset of the real numbers. And we're going to suppose that E is both closed in the sense of the last section and is bounded. So the infimum of E and the supremum of E are both finite. And let's let F be a function whose domain is E and whose range is the real numbers. And we're going to suppose that F is continuous at E for every point little e in our set E. So F is continuous at every point in E. Sometimes we say F is continuous on E if we mean that F is continuous at every point in E. And then the conclusion is that there are two numbers that are both in E. I suppose I ought to explicitly say that E is not allowed to be the empty set here, because the empty set is closed and bounded, but certainly there do not exist any numbers at all in the empty set such that f of x naught less than or equal to f of E less than or equal to f of y naught for all E in our set E. And then in particular, we have that the supremum of all the values of f that's going to have to be f of y naught. F of y naught is an upper bound, and it's obviously the smallest upper bound because it's also an element of this set. That is finite. So let me draw this picture for you. So a function on an open interval, something like like f of x is 1 over x, and E is a non-closed set, like this open interval from 0 to infinity, that can go off to infinity, so it doesn't have a maximum. This is bounded from below here, but you'll notice that the lower bound is 0, and 1 over x never actually gets to 0. And what we're saying in this theorem is that this cannot happen with a closed and bounded set. Let's go ahead and prove this. So let's let T be, let's say, the infimum of our set of all f of E such that E is in E. And I'll just prove the infimum case, the lower bound case, and we'll leave the upper bound case as an exercise or an exam problem or something. And then if n is a natural number, then T plus 1 over n is not a lower bound. Now, and this is T bigger than minus infinity. And if T is in fact minus infinity, then minus n is not a lower bound. And so there is some, let's call it xn in E, with f of xn less than T plus 1 over n, or in the case where T is negative infinity, f of xn in this case is going to be less than negative n. Now we're going to see that T can't be minus infinity, but we haven't proven it yet, so we have to keep that in mind as a possibility until we do get around to proving it. And because T is the infimum, we've always got that T less than or equal to f of n. So in either case, we have that f of xn, that's a sequence that's converging to T. If T is minus infinity, then our sequence is converging to minus infinity in the special definition for that we gave. Now, E is bounded, so E is contained in some closed interval, say from L to U, where L is the lower bound for E, U is an upper bound for E. For some LU, they're real numbers, meaning they are in fact finite. And that means that our sequence of xn's that's contained in E is contained in LU. So we know any sequence of points in a closed bounded interval, so by Bolzano-Weierstrass, there is a convergent subsequence. It converges to some point x in the real numbers. But remember, E is closed. And our xn's, so of course our xnk is, because it's a subsequence, they're all xn's, that is a subset of E. So the limit x has to also be in E. Then we have that f is continuous at x because x and E and f is continuous everywhere. And our subsequence x and k converges to x. So f of x and k is converging to f of x. But f of x and k is also converging to our lower bound t. That was our infimum of the f of e's. So f of x is equal to t. And so there is a point x such that f of x is the infimum, and in particular, since f of x is not minus infinity, the infimum is indeed going to also not be minus infinity, is going to be finite. So now let's state a corollary to the extreme value theorem. So let's let E be a subset, the real numbers be a closed and bounded subset of the real numbers. And we're going to let f be a function from E to the real numbers, and we're going to assume that f is continuous. Then f of E, this is the image of f. This is the set of all f of E such that E is in E. That is also both closed and bounded. And the proof of this is pretty straightforward. That is why it is a corollary. So by the extreme value theorem, all right, if E is empty, then obviously f of E is also the empty set, so that's closed and bounded. So if E is not the empty set, then there are some numbers, probably two numbers. They might be the same if f is constant, but there are some x in E such that f of x less than or equal to f of E less than or equal to f of y for all little e in our set E. And then since f goes from E to the real numbers, f of x and f of y are finite, so f of E is bounded. F of x is a lower bound, f of y is an upper bound. And then now let's suppose, now we need to show that f of E is bounded. So let's suppose that we've got some sequence of points that's contained in our set f of E, and yn is converging to some target number y, then each yn is f of x sub n for some x sub n in E. So that's what f of E means. It's the f's of something. So each yn is f of x sub n. But remember, E is bounded. So by Bolzano, Weierstrass, there is a subsequence let's write that x sub n sub k equals 1 to infinity. Notice that this is also a subset of E, with x sub n sub k converging to, actually I'm going to name the limit E instead of x because I've already used x for the lower bound back when we were showing this was bounded. And then E is closed, and this subsequence is a subsequence is a sequence. So we've got a sequence in E that converges to E. So our little e, our limit point, is in E. F is continuous. If we just say it's continuous, then it's continuous everywhere. So in particular, it's continuous at E. So f of x sub n sub k is converging to f of E. But f of x sub n sub k is a subsequence of our sequence f of x sub n, which is also known as our original sequence y. So f of x sub n sub k converges to y. So the conclusion is that y equals f of E, which is therefore in f of E. Thus, E is closed. And the thing I want to point out here is we have in fact used the fact that E is closed and bounded to prove that f of E, f of E is closed. To prove that f of E is closed, we needed to use that E was closed to get little e and E, but we also needed that E was bounded so we could use Bolzano-Weierstrass. So, and we do in fact need that. If we didn't have the closed, if we had just a closed subset, you can send a closed subset to a subset that's not closed. And similarly, if we just had bounded but not closed, there are all kinds of continuous functions that end up bounded sets to unbounded sets. For example, 1 over x sends the interval from 0 to 1 to the interval from 1 to infinity, which is unbounded. To talk about one more way to put together continuous functions to make a continuous function. So here is definition 1.7.9. So let's let x be a subset of the real numbers, and we're going to let f and g both be functions whose domain is x and whose range is all of real numbers. And then we are going to define the following two pieces of notation. this is our notation for the minimum, whichever is smaller, of f of x and g of x. And this is going to be our notation for whichever of them is bigger. And now here is a proposition about this sort of maximum and minimum thinking. So we're going to pick a domain in the real numbers and two functions from that domain into real numbers. And let's suppose that f and g are both continuous at the point, let's say, little x in x. Then these two functions, the max and min of f and g, are also continuous at our point x. And the proof is pretty straightforward. I'll put up the proof just for the maximum case. And you can probably work out how to prove this for the minimum. So let's let xn be a sequence of points in x that converge to our target point x. And because f and g are continuous, we have that f of x sub n is converging to f of x, and also g of x sub n is converging to g of x. All right, now what we're going to do is we're going to direct our reader to pick a positive epsilon. And we're going to let n1 be a natural number, be such that if little n is bigger than n1, then f of xn minus f of x in absolute value is less than epsilon. And I'll point out to you this is equivalent to if n is bigger than big N1, then f of x minus epsilon is less than f of xn is less than f of x plus epsilon. And we're going to let n2 do the same thing, only for our function g. And we're going to let capital N be whichever is bigger, N1 or N2. Pretty standard trick in analysis. You take N1 and N2 that both do the thing you want, and then you take the bigger one, and then both of them are going to work. And then if little n is bigger than big N, then let's write this out. We're going to take the maximum of f and g of xn. And then notice that f of xn, because n is bigger than big N, which is bigger than n1, f of xn can't be any smaller than f of x minus epsilon. And g of xn can't be any smaller than g of x minus epsilon. And then notice we can move a minus epsilon out. This thing is precisely equal to max of f of x g of x minus epsilon, which we write with our v notation, f v g of x minus epsilon. And then pretty much exactly the same going in the other direction. Similarly, f wedge f v g of x is less than of xn, is less than f v g of x plus epsilon. So we can turn this back into absolute values again. This thing is less than epsilon. And so putting this all together, you pick an epsilon, then there is a natural number n, such that if little n is bigger than big N, then FVG of xn is within FVG of x. So the conclusion is that FVG of xn, that is converging to FVG of x. And this is true for any sequence of xn's that are converging to x. So we get that FVG is continuous at x. And that completes the proof.